Greetings, everybody. This is Dr. Gomez. This video will go over the solutions to your practice final, which is posted. The practice final and the solutions are already posted on Georgia View. And I might break this video up into 2 or 3 parts, depending upon how long it is. And your final, the format will be the same in terms of the content of the questions. They won't be the same questions, but they're going to be very similar. So, for example, question 1 is back from the material from exam 1, and it's remember what we call the Head Start problems. And what you have is two bicyclists. We'll call them bike A and bike B. And bike A is riding his bike at a speed of 2 meters per second when his friend on bike B rides by him or her at a constant speed of 3.5 meters per second. So the key is bike B in the green here. Bike B is moving at a constant speed. And what happens is he passes bike A at this point here. And because he's moving faster, he's moving at 3.5, bike A is moving at 2. Because he's moving faster, he's going to get ahead of bike A. And then what bike A is going to do is, after this reaction time of 0.9 seconds, A accelerates at this 2.4 meters per second squared until he catches his friend. So what happens is, because B is moving faster in the green, during that reaction time of 0.9 seconds, he's going to get what we call a head start. He's going to be ahead of bike A. Then after the reaction time, right here, bike A begins to accelerate, and eventually over here, he's going to catch up to his friend. And so both bikes travel this distance of x. And so remember, how do we set this up? Well, notice here's bike A moving at some v initial, which we know. Here's bike B moving at the constant speed of v. Well, during the reaction time, each bike is going to move a certain distance during that same reaction time. I'll call it TR. And so I'm going to call the distance that A moves during that reaction time, I'm going to call that dA. The distance that bike B moves during that same reaction time, that's dB. Okay. Then after the reaction time, the bikes still continue to move. Well, the remaining distance that bike A moves will be given by kinematic equation 1, v initial, because now he's accelerating. So the remaining distance is given by v initial plus 1/2 at squared. The remaining distance that bike B travels, remember bike B is moving at a constant speed, v. We don't need a subscript. There's no vi and vf for bike B because he is moving at a constant speed. So during the remaining time, the distance bike B moves is v times t. And remember, our goal is first, we already know TR. Our goal is, remember, to get VT. Not VT, just T. Okay. Well, now notice. So the distance that A moves during the reaction time, dA, that's VI times TR. Just distance is speed times the time. Plug in the numbers, you get 1.8. The distance that B moves, dB, is just V times TR. Nothing complicated. Okay, so now that allows you to get dA and dB. Then remember, now look at the diagram. Well, just set the distance that A travels, the total distance x, because they both move the same distance x. So just look at the expressions for the total distance x. Just look at the blue. You have dA, your x is equal to dA plus VIT plus 1/2 at squared. Just look at the blue equation. Then look at the distance, the same distance x for bike B. That distance is dB plus VT. So you want to set them equal right here. Then what you want to do, and again, we already know what dA and dB are. Then what you want to do, so you have here, so you have dA plus VIT plus 1/2 AT squared equals dB plus VT. Now you want to rearrange this equation algebraically, basic algebra, it's not complicated at all. You want to rearrange it to get a quadratic equation in T. And right here, and you get 1/2 AT squared plus parentheses VI minus V times T plus parentheses dA minus dB equals 0. Now we know A, we know VI, we know V, we know dA, we know dB. Put in the values and you get your three coefficients for the quadratic equation. You get 1.2 T squared minus 1.5 T minus 1.35 equals 0. Then just bring up a solver. If you have one on your calculator, fine. If you want to bring one up online, this is not an algebra class. We all know how to solve a quadratic equation. You're going to get two roots for T. You're going to get, in this case, 1.86 seconds and a negative 0.606 seconds. Well, we can't have a negative time, so you get rid of that. Now remember, that's our goal. Now that we know T, let's look at part B of the question. How far, well, both bikes travel the same distance x. I want to know how far does either bike travel? I want to know what is x. Well, I could use either the green equation or the blue equation to get x because they're equal. Well, the green looks a little bit easier, so why don't I just use, for part B, x is equal to dB plus VT. Plug in the values, you get 9.66 meters. Now, you don't have to do this, but if you want to check it with the blue equation, the equation for bike A, x is dA plus VIT plus 1/2 AT squared. It doesn't take too long to check. And you notice here I get 9.66 meters. Here I get 9.67, close enough. Okay. Then let's look at part C. What is the speed when he catches his friend? Meaning I want to know what is the final speed of bike A. Well, I want to use the second kinematic equation, VF equals VI plus AT. Because remember, in this case, bike B moving at the constant speed, i.e. his speed never changes. So you get VF equals VI plus AT, and you get, plug in your numbers and you get your value. So that's there's plenty of Head Start problems in the notes, and you can go through this one. It shouldn't be too bad. Let me look at problem 2, and then I'll do another video. Well, problem 2 is a very straightforward static equilibrium problem, where you have this uniform beam of length little l. You know little l. You know the weight of the beam. The weight of the beam itself, and it's attached to the wall over here. By now, you should all know that's going to be my pivot. When I do the sum of the torques, the far end of the beam, the one farthest from the wall, it's supported by a cable. The cable makes an angle of phi with the beam. That angle is 53 degrees. We're given phi. Then you have a person. We'll call the person's weight WP, 600 newtons. And again, we know the weight of the beam itself. We know the length of the beam, and we know the weight of the beam is the 200 newtons. We know the weight of the person is 600 newtons. We know the angle. We know L. We know D. So the person's distance D from the wall. And I want to find two things. And I noticed on exam 4, some of you did not complete it. You didn't solve for the reaction force completely. You must have misread the instructions. But anyway, so I want to find the tension in the cable T, and I want the magnitude and direction of the reaction force. That's the force that the wall exerts on the beam right at that pivot. Well, remember, the rubric never changes. First, let's go ahead and pause this for a second again. So what we want to do is first, let's draw all the forces, because remember, the beam is the object that's in static equilibrium. So we're applying the static equilibrium conditions to the beam. So let's draw all the forces acting on the beam and also make sure to get their x and y components. Well, I'm just going to go from the right end of the beam, and I'm just going to go right to left. So there's the tension force acting on the beam. Remember, it's directed along the cable and away from the beam. That's T. Well, T has an x component and a y component, nothing complicated. The x component is T cosine phi. The y component is t sine phi. Notice the x component of the tension force. Notice t cosine phi is in the negative x direction. Okay. Now let's go to the weight of the beam itself. Well, remember, it's a uniform beam, so we know the weight acts at the exact center of the beam, WB. And we know it's at a distance of L over 2 from the pivot. Now, weight of the person, WP. And we know the person is at a distance D from the pivot. Well, now the reaction force. And remember, you always draw the reaction force as if it's in quadrant 1. So that's R, the purple force vector indicated there. And R has an X component we call Rx, a Y component we call Ry, and I use alpha to indicate the angle, i.e. the direction of the reaction force. Remember, when I say magnitude and direction of the reaction force, by direction I mean angle and quadrant. And we assume it's the reaction force is in Q1. Okay, so now I have all the forces. Apply these static equilibrium conditions. And remember, always apply them in this order. Sum of the forces in the y direction equals 0. Get equation 1. Sum of the forces in the x direction equals 0. That's going to give you equation 2. Sum of the torques about your pivot, which we know by now that the pivot is where the beam is attached to the wall. Sum of the torques is equal to 0, and that's going to give you equation 3. Well, let's look at the sum of the forces in the y direction. Well, that's the green. There's 4 of them. T sine phi and Ry, they are positive. The two weights, WB and WP, are negative. Add them up. T sine phi plus Ry minus WB minus WP equals 0. It's equation 1. Okay? Sum of the forces in the x direction equals 0. Well, there's 2 forces in the x direction, Rx and T cosine phi. Well, clearly Rx is positive, T cosine phi is negative. So, sum of the forces in the x direction equals 0. Rx minus T cosine phi equals 0. That's equation 2. Or equivalently, you could write right away Rx equals T cosine phi. Not a big deal. Now let's do the sum of the torques about our pivot, indicated by the black dot there. The sum of the torques equals 0. Well, so now just remember, if the beam, imagine if the beam were free to rotate about that pivot, the tension force will create a counterclockwise rotation. By definition, that's a positive torque. The two weights will create a clockwise rotation. By definition, those are negative torques. And the reaction force creates no torque. Any force that acts at the pivot creates no torque. So, sum of the torques. Remember, well, what's the torque to the tension force? Well, in general, it's Rf sine theta, where R is the lever arm. F, that's the general formula. That's a general formula. So, well, so what's T? Well, the force, let's look at T. The force is T. We're looking now at equation 3. The lever arm is small l because that's the distance from the tension force to the pivot, small l, and is sine of phi. So the torque due to the tension is positive, TL sine phi. Well, the torque, now let's look at the two weights. Well, WB. Well, clearly by now you know that WB, it makes an angle, and its lever arm is L over 2, half the length of the beam, because it acts at the center of mass, which is at the midpoint. Well, so the force is WB, the lever arm is L over 2, and remember the angle is 90 degrees, and the sine of 90 is 1. So you have, so it's a negative WB L over 2. But likewise for the weight of the person, the force is WP, the distance is D, and again the angle is clearly 90 degrees. The angle between WP and D is 90, sine 91. So again you have TL sine phi minus WB L over 2 minus WPD equals 0. That gives you equation 3. Now remember, then the rubric, follow the rubric. It never changes. Don't make this a problem more difficult than it needs to be. You solve equation 3 for the tension, then solve equation 2 for Rx, then solve equation 1 for Ry. Never changes. So now algebraically, you can all do the algebra. You get this expression for T, and you get your 313 newtons. Then then just go backwards. Solve 3 for t, 2 for rx, 1 for ry, in that order. Well, again, rx is t cosine phi, which gives you 188 newtons. Then solve equation 1 for ry. You get this expression for ry, and you get 550 newtons. Then you're not done. I want for the reaction force, I want the magnitude, i.e. the hypotenuse, Pythagorean theorem, and I want the angle alpha. Well, I know because, so I know I got Rx and Ry. Well, Pythagorean theorem gives me the magnitude of R, and alpha gives me the angle. Inverse tan gives me the angle. I misspoke. Alpha is equal to the inverse arctan of Ry over Rx. Plug in your numbers. You get R is 581 newtons. Alpha is 71.1 degrees. And it's Q1, but this is fine. So that's problems 1 and 2. And so on the final, problem 1 is going to be a head start problem. And problem 2 on the final will be a static equilibrium problem. Let me go ahead and save this video, and then I'll post another video again, I might break it into more than one, but then I'll post videos for problems 3 and 4.